1.1, 1.3 meter. Right?
The lowest.
Huh? Yeah, lowest point, roughly because of our design pressure, right? So it's about this range. And then your VM 0.1 something, right? 0.1 something to nearly 0.2 something. Okay. So of course, different group you might find different values, but roughly around the range. Right? So what happens is after you get this, you must use your own student number. Alright, you substitute your this corrosion value, followed by 133 megapascal because the material we use megapascal, right? Then you substitute the diameter here. Then you will find your VM. Now that one is actual VM. We will use to build your FS. Okay.
So, 133 should be different.
Yeah. So what? Okay, sorry, 133. This is a P. Right. 0.85. Then we are able to determine the VM. So this VM equals to what? Equal to your actual. Later on, you have to find out how much sheet metal to use. Right? How much sheet metal to use in order to build this FS based on this value. Of course, you have to find out the length. Right? Just last week we actually discussed the length of the vessel with the diameter. Then you know, right? Anyone still have any issue with this? Question 3. Once you know this, you just plot according to the question require you to do, right? Various corrosion allowance 1 to something, right? Various tensile strength 115 all the way to 130. Just to explain, allow you to explain this different corrosion value as well as tensile strength will impact the diameter. Alright, whether thickness, alright, it will impact your diameter used on the vessel itself. So you have to explain this from the graph. Okay, so let us go through this because today I need to cover flanges, especially for this question, right? Now we want to talk about the question here. So I believe for question 3, just now you try, I saw some of you, the working shouldn't be any problem now. Question 4 easy, alright, question 4 just 1 mark. Basically you go to this, the AS 1210. Alright, clause 3.5.1 is my answer. So question 5, last week explained, alright, we talk about the opening, alright, opening. So for this week we want to talk about after opening. So imagine this is our vessel. After you, alright, you actually cut the opening. So after you cut the opening, you want to know this is your cutaway area, right? Cutaway area. So if let's say side view is like this, let's say this is your. After that, we have to insert the pipe. So let's say this is your vessel, right? Then you cut the hole here. You are going to insert a pipe, right? This pipe. into this vessel. So this is a vessel. Or shell, they call this as shell. Right? So this is your nozzle or pipe. So this is the cutaway area that you have. Cutaway, right? So as you know, right, later on after you calculate, right, your diameter, vessel diameter as a VM, alright, then you have to calculate the thickness. Thickness is, the other day we talked about thickness is, alright, so this thickness equal to alright, so this thickness is actually the thickness that withstand the design pressure. Alright. So this is important. Why? Because when we come to this opening, right? So we know that this the shell or the thickness of the vessel, alright, is actually able to withstand more than your design pressure. Let's say your design pressure, this T, let's say 4 mm, right? You go to the catalog, you don't find 4 mm because 2T. So let's say catalog show 10 mm, means what? Means now, alright, our shell here is 10 mm, right? But your T that can withstand, right, withstand the pressure is 4 mm. So they represent it with the capital T. This is small t. Okay. And what happened is this area that we cut away, over here this area, can be compensated by the area here. This area is called A1. Alright, called A1 divided by 2. And then for the nozzle, right? For our project, we will find the nozzle same thickness as our vessel. Alright, so let's say this 10 mm, this one also 10 mm. Example can be more. As example, this 10 mm again. Alright. So you have what we call A2 area. A2. This A2, because this 10 mm is actually thicker, right? Thicker than your design pressure. Right? Let's say your design pressure 4 mm. In this case, we are able to use this part to compensate the cutaway area, because we have this excessive, right, area that able to compensate. So this is how we get A2, right? A2. And then if let's say your nozzle insert beyond the vessel, let's say this is you insert deeper, alright? So in this case, this is called A3. Right? The area that covered under this vessel is called A3. So now I'm explaining to you what is A1, what is A2, what is A3. A4 are those welding. Alright, example, let's say now this is the nozzle, this is the vessel, right? You need to weld it, we need to weld them together. So it is called A4. Right? After that, A5, if let's say after you total up this area A1, right, your area A1 plus A2 plus A3 plus A4 must be greater than or equal to your A. So A is the one that you cut away. Right? A is the one that cut away must be greater. Means what? Sufficient. We are able to compensate sufficiently the area that you cut away. So your vessel will be safer. But if let's say your A1 plus A2 plus A3 plus A4 is smaller than your A, you have to use reinforcing ring. We call this enforcing ring is called A5. So this reinforcing ring will actually enforce means enhance, alright, such that you are able to increase the area to compensate the losing area of A. Okay. Okay, so with this idea, then we know we can do your question 5. Alright. Okay, now come to the next your partner for the same question, right? Because this question, partner 1 do A, B, C, D. Partner 2 do E, F, G, H. So now we come to the flange. Alright. After you insert the pipe, let's say side view here. So this is opening, right? Let's say now you actually insert a nozzle for manhole. Then in this case you need to cover. This is a flange, you have to find a flange able to cover the nozzle. Alright? And this flange will have the bolt. Right? The bolt and the gasket covered. Why? Because our air vessel, right? Design pressure 862, right? 862 kilopascal. When compressor is running, alright, so you can see the pressure actually press against your nozzle, right? Press against nozzle. So the force, okay, so let's say now I show you between the nozzle, let's say this is a nozzle, this is your flange. In between you have a bolt, secure. In between them is a gasket. Alright. So imagine when the compressor is running, the force actually push, right? Push the plate up, right? Let's say now you have a compressor running, the force will push the plate because the plate is covering the nozzle or the pipe. Higher pressure, it will press against this cover, or we call this flange. Right? So what happened to your gasket? If let's say now the pressure push against, because we are securing this, the flange covered with the bolt, right? So this is your bolt, the nut is here, the nut is here. So this is your bolt. So if let's say without this, we call this pressure hydrostatic. Hydrostatic pressure. Hydrostatic. Right, can be fluid or air, right? But our project is air, right? So without compressor running, let's say no pressure, so you secure, right, your the plate with the bolt, and then the gasket will be compressed, right? The gasket, because there's no force push against them. But when there is a pressure run by the compressor, now the force will compress, right, from the other side against the bolt, right? So in this case, your gasket, instead of compressed, right, because of the force coming from the internal vessel, so it will decompress a bit, right? Because they go against the bolt force, the gasket will decompress a bit, right? So this one exactly our learning package. So this chapter 6 actually shows us what I explained to you. Alright, you can see the cover like this one, right? So with the bolt, cover the pipe, And ours is very similar to this. Right? We have a nozzle here, so the flange cover. You want the cover tighten with the bolt. Right? When there's a pressure from inside, compressor is running, it will push against. Right? Push against this cover plate. And then over here, our project is using the full face gasket. According to our question asked, they actually show us you need to use full face gasket. And this is your raised face, right? And this one is the narrow, we call this a ring groove, right? So ours is this part. We are using this full face gasket for our project. Alright, so this is what I explained to you. Alright, you have your hydrostatic end force. When you tighten the bolt, alright, so this is the bolt force. Oh, sorry, this is the blue one. This is hydrostatic. Alright, Hydrostatic means the pressure from the vessel itself. Of course, when compressor is not running, you don't have this, right? So this is your boat force, gasket reaction force. When you tighten, all right, so you will compress the gasket. But when there's a hydrostatic force, it will push against the boat. So in this case, your gasket, instead of compressive right now, become decompressive because of the force against the boat force. All right, so this is I explained to you just now. And this is what happened looking at the graph. Let's say without the pressure from the vessel itself, when you tighten the bolt, all right, you will see the gasket compress. But when there is a hydrostatic force, you can see the decompress of your gasket a little bit because of the hydrostatic force from the vessel itself. Right? So the graph actually shows you the force pattern with or without the hydrostatic. Right? So important is to look at this operating and sitting for this question. Operating and sitting. Sitting means without hydrostatic, you tighten the bolt. Alright, so this one, you tighten the bolt. So your gasket is compressive. Operating means hydrostatic. Right, means you have this pressure from the vessel itself. Right, so for this question, you need to know these two things. Alright, and some of these the defects. If let's say you tighten too much, alright, over tighten. Of course, you can see right, you tighten too much, you actually cause this plate to deform. Means what? Means now the gasket cannot contain the pressure. Alright, so you have a leaking. We call this a flange bowing. Alright, so over here they show us for the full face flange, the one that we use. Alright, so you have this notation. Alright, so notation can be found from your AS1210. Okay, over here they just show you the plate, and then this is the gasket, and then the bolt. Alright, and then this is the design of our flange. Alright, so over here is your nozzle. Alright, so how the distance, alright, between the gasket and the nozzle, alright, you need to know for calculation wise. This is what happened. Right. This is a narrow face flange. If you have time, you can go through because ours is a full face. Alright, so I just had to highlight is this sitting. During sitting hydrostatic force, H is not present. Alright. Then another one scenario is operating. During operation, hydrostatic and force H is present. So you have to differentiate between the two for your to answer your question and to answer your project. Alright, so this is a nice picture. Alright, so this is a gasket, and then this is the cover or the flange. Then this is the bolt securing the nut, right? Tighten such that we are able to compress the gasket to prevent leaking. So W is the loop, right? And then this HD, right, is the force from this hydrostatic, right? Then HD, the small HD is the distance from the nozzle to the center of the bolt. Alright, so over here you can go through the details yourself. Okay, so now we have to go back to your project. Look at the question asked, what they want from you now, right? So for the partner Y, alright, you have to start with the question F here. Part 1, check the center to center spacing of the boat on the pitch circle is not too great. How do we tell? You have to apply the formula here. We go to the clause 3.21.4.1. Alright, so you need to apply this formula. So you make a note, I mean easier for the partner Y. Later how to do question, you have to apply this formula. Alright. So now I'm going to tell you what are the values to use. Alright, so your E is your young modulus. Equal to 198 gigapascal. Alright, equal to 198,000 megapascal. So we use this value for this question, right? So thickness, you can find out thickness from this the flange cover. So M value thickness 35. Alright, so the M value is 0.8. Right, for this question, 0.8. Of course, if you want to know notation, you have to scroll down, scroll up to see what is M for. Alright, M is Gasket factor. Alright, so we use rubber wrap or elastomer request by your questions, 0.40, the gasket factor. Table 3.21.6. Table 3.21. over here like they use 3.1.6.4. Right, gasket factor. Okay, so next thing is to decide, right, what type of flange we use. All right. Label 3 form. Alright, okay, so here is why I use 0.8 is this factor. Right, gasket material and suggested contact factors is 0.8. Because we use rubber for this part. So by using this formula, okay, once you find out this, the distance, right, maximum distance. So you want to find out the flange that actually lower than this. This is a maximum, the distance between, right, the spacers. So it is recommended the work spacing on unproven flange design be not greater than the dimension obtained from the following equation. Okay, so in this case, you have to substitute, right? So now where can we get this diameter? of your book. So we have to come here. Alright, so common book sizes. Over here we will use M24. Alright. Size and pitch 3 mm. If you look into this, this is your inches, right? Inches. So we are using this M24, the size for our project. Okay, so we go into the table B3, right? Table B3. Right, table B3 will give you these young modulus. So ours is 190. Titanium, copper. Alright, over here 190. Well, this is the value we get. Temperature, ours is 100 degrees Celsius, right? Alright, so this is, now I want to find is, where to find the book. Determine the required book force both for this. Okay, so I need to go to this AS2129. Okay, so we come to this part. Can you download this A1 AS2129 from Canvas? Okay, so just to share with you, partner, second partner, you have to use this flash table E. Alright, so this is a temperature range within our 20 degrees Celsius to 100. Alright, so we use this one. Of course, you can see higher the temperature, the value decrease. Alright, but we are in the range here. And over here is the maximum allowable hydrostatic test pressure kilopascal. So what is our hydrostatic test? Second question. 1.43, right? I don't know, use the formula. Huh? What is your hydrostatic test?
1,200 kilopascal.
1,200. 1.2 megapascal.
Yeah, 1.2 megapascal.
So within the range here, within the range. Okay, so next we want to find out more details about our flange cover. Appendix 16. Alright, so this is where you get your details. What are the, how many bolts we use, right, for our cover, and also diameter of the flange, pitch circle diameter, number of bolt, diameter of bolt, diameter of holes. All this important. So which one do we select? When come to the flange, under this, so our is E, right? E. Yes, so we use 450 mm because our opening, what is our opening size? Remember the opening size 450 mm according to your student number, right? So it varies. So definitely more than 450 I mean we are able to use 450 mm here. So just now I mentioned about E, right? Pass E. So over here you need to take this, diameter of flange is 640. Alright. After that, H circle diameter. .584. All this is important because without this you cannot do your question. How many volts? 16. Alright, diameter of both 24 mm. Alright, and the diameter of the hole 26. Of course, your hole must be bigger, right? And thickness of the flange is about 35 mm. Okay, so later you need to use all this information for this question. Alright, then after that, followed by, after we know all this, then we have to check there is adequate spanner room. Because as you know, right, spanner, you need to tighten the bolt. If let's say no allowance, no point. So you must check whether any clearance or not for this spanner to actually tighten, alright, our bolt. So refer to tables for spanner or wrench clearance given in the E-reverse or E-reserve reference activity 6F. So you try to find whether 6F available. Okay, so this one you can see. After you get all this detail right, you can find from here whether the clearance sufficient for us, right, to tighten the bolt or to untighten at the same time. Alright, so mainly we will use this. Alright, so we have various type of wrenches as well. So you can explain, right, whether you use 6 point or 12 point, you can explain via these. Because the diameter we know, right, the bolt size we know, diameter we know, so we are able to use this to explain yourself for this question. Alright, so the third question, determine the required work forces both for operating condition and sitting condition, right? Just now I mentioned, right, important is the two scenarios. Operating means the pressure from the vessel. Alright, you have hydrostatic pressure. Sitting means no pressure, only you tighten the bolt. Alright, so those are called sitting condition. So now we want to find out more, we go to this source. Alright, so over here, all the notation you need to know, because when you do this question, right, if you still lost, you come here to look at this notation. Important is to identify this HG, capital H or smaller h. And and all these are the moment, mg, all this, w, wm1, wm2, all these help you to do the question. Okay, now to come to this question, alright. Just now we want to know the boat force, whether sufficient or not. You have to apply this formula. Alright, you have to apply this formula. It sounds complicated at this moment, but all this notation, right, when you fall back to just now, the list, actually quite straightforward. Quite straightforward. You just need to apply this formula. But for this, as you know, the gasket that we use is gasket sometimes this area, right, AP, MP, B, right. So we take this as a 0 for the partner Y. This AP, MP, AP for this, our gasket use, there's no bypass. Some gasket, if you look at it, they call this, there's some, they allow some liquid or fluid to go through. Right? But ours, full gasket means that there's no bypass. Right? No bypass. This one equal to 0. You just need to use this formula. Okay, so for you, you need to identify for operating means with the hydrostatic is WM1, right? WM1 for operating. For non-operating or sitting condition is WM2. Alright, so this is how you do this question, operating, sitting. Alright, from this equation. After that, confirm adequacy of total boat chord area, assuming precision matrix steerboat, alright, of grade 5.6 or 8.8 value. So this one we have to go into table B2. Table B2. Right, over here you can see, right, 5.6 and 8.8, right, just now dimension. So we have to use table B2 here for this question. So the question asks this, right, confirm adequacy of total both chord area for grade 5.6 or 8.8. So in this case, you have to come here. And then look into this, the value here, 5.6, 8.8 is actually the tensile strength they want you to look at. One is 75 at 50 degrees Celsius, one is 160 megapascal, 175. You need to know these two values in order to find out later which one to use. Right, which one to use. So table B2 important to you. Because you want to find total area, right, of the book, whether adequate or not. And then part 5, determine required tightening torque for the book. Alright, so for the torque value, T equal to KDF. You just write down for this question, right? The torque value is KDF. Alright, so K is 0.2. It's actually the material used for the pole. So over here, zinc plated 0.2, and then the diameter just now we mentioned. Alright, diameter here 24 mm. So 0.024. So F, you have to find yourself, F.
So the F is just now you thought that for the 75 or 160.
Because F actually you have to use from WM2. Right, WM2, just I show you, right, WM2, in order to find out the F. Alright, so it's a both force, come to sitting, right? Come to sitting, both force. Okay, so this is part F. Now we come to the G, alright? Regarding the flange stresses, determine the bulk force that may exist during sitting. So sitting means no hydrostatic, right? So the stress. Now our idea is to find out the radial flange stress. Alright, so if you go to this the clause, they will tell you how to find this SR, the stress, radial stress. So let us take a look at this both force exists during the sitting. Right, 2, 1, 11, 4. So we use this formula for the radial flange stress. So over here, this is for the seating. Alright, for this question, without hydrostatic. Part 2, operating condition with hydrostatic. Refer to the equation you can find out. As well as the tilting moment. So what happens is this, right? If let's say this is your flange cover, alright? So what happens is the book secured. If let's say there is pressure coming out from this vessel itself, if let's say this one if you don't tighten properly, right? Let's say this one is loosening, so you will have pressure in a set here. There will be a moment, right? Because this part is let's say not secured thoroughly, so there will be a moment the plate try to open up, right? Then you have the bending moment. In this case, bending moment from here. So over here allow us to calculate out the tilting moment, right? For this scenario, So you have to identify, alright, the moment there's an MG and O. When you work on this, you will see the difference between the two. So you have to identify them. Alright. And lastly will be the tangential flange stress. Look into the equation, alright, then you can find out easily. So determine appropriate welding arrangement for attaching the slip or flange to the pipe piece. Welding. So you can go to the clause here. On the diagram you can select which one more appropriate. Confirm adequacy of the cover plate. Right. So those are for the partner Y. Alright, doing this the flange cover. Okay, so these are the questions. So question 6 we will discuss next week regarding the support, the column, lugs and the pads. Right. So right now, to give you some idea what are the things that you need to do, right? I have some exercises here to help you, right? Okay, so for partner X, right, we try to familiarize ourselves with this because this question also my favorite question for exam as well. Alright, although the partner Y don't do this question, but during exam you might actually have this type of cutaway opening. Alright, they want you to actually calculate area, right? So now just familiarize ourselves with this question. Determine area A means this part that's going to be cut away. Alright. So what happened is given design pressure, I want to exercise will be different from your project, right? So but approach will be the same. Diameter of vessel, corrosion allowance 2 mm. Alright, the steel strength is 133 megapascal. Joint efficiency is 1. And then this is the pipe size. Diameter of the pipe size is 400 mm. Also, opening is actually opening of it. So determine area A1. A1 is this part, right? A1. And the shell thickness is this. Shell thickness is your shell thickness. So determine area A. Alright, determine area A. So let me write the formula on the board here so you can proceed with this. Alright, so A equal to dt. Alright, so the trick is you need to find out the T, right, that can withstand the design pressure. So what is the formula for this T? So please spend some time just to familiarize the approach. Sometimes because if you substitute more feel the series.
This one.
And from 0.1 to 3 meters.
Then in between, just change everything. Then I think this shape, but we put like this one by one.
So this is our strength.
Yeah, that doesn't just change. If this one change, then cannot.
Because so what happens is that's why I show you let's say you fix your then integrate your graph in various tensile strength.
Yeah, that's why I put it here. This one I'm going to change. this shape, we must face this one, cannot so to show uniform, we have to show about this. So can we just do this?
This card is 1.5, this card is 1.0. So what I suggest is maybe you fix your then you vary the diameter is 1 cm. Then you show this for you. Because I need to see this will become easy.
So we want to see like this. Form like this. Now, then
You see our question one we ask you to do is that you fix your corrosion, you vary your tensile strength. All you can vary, you can fix your tensile strength, vary your corrosion. You want to see the relationship.
cannot make it like this much because you have only 5 then we can get the shape like this. Because we have only 5 means it's bigger like this. This one is a variable tensor. And if you fit this one, right, we have only 5 to 10.
HD finish already.
Hmm?
The HD.
How do you go back
They
already?
go back already.
Yeah, I thought HD is our the Indian cultural. He every time very soon on there like 10 o'clock.
I think the the 9:30. Actually, I
Huh?
31:30.
Why they got so special timing one?
Don't know.
Or maybe they with the new batch. Then the new batch they change already. Maybe they got like
Probably like 10. Can you send me the picture?
Sure. Oh, this one? Yeah, sure.
You did for me.
But you know that but now you know that you know the diameter, right? All that diameter is the diameter of the so what is the
That's the formula.
Yeah. But very confusing, like the formula give. I mean, they say here is given T, then he asked us to calculate T again.
Error.
okay, so can you get answer for A and A1?
Oh, that's A1. Oh, okay, okay.
So what is your A value? What do you think? The cut away area. So you can say cut away area is T, right? Then this is your correct 400 mm, correct? 0.4 m. Then your T, so A is what? A is your
1.37.
so what's the T value?
3.4256 10 to power minus negative 3.
So it's mm, right? Mm. So 3.4 mm times your 0.4 meter. So this is the cutaway area. Uh, 0.4. Oh, actually, we can also use the 400 mm because for this question. Times 3.437. Right, so area will be 3. Alright, so this is the answer. Because from here, right, this is your design pressure, is 0.79, right? Times your diameter given is 1.15, right? Then to efficiency 1, then tensile strength 133, right? Minus 0.7. Right, so this is the thickness that withstand pressure, design pressure. That's what they show here. Your actual thickness of the vessel, material that you opt for, right, material that you choose is actually T1. Alright, so this one I need you to know why the T is important for this type of question. Because T1 is the material that you choose. This smaller T is the thickness that withstand pressure. That's why we have excess of this. Right, excess of this means this is our A1. Right, excess of this area can compensate the cutting here. We use to compensate, right?
So, sorry, the
9375.
that one is from which formula?
Oh, sorry, 3.4375. From here,
3.425.
3.4375 from here. I don't know if you calculate, you should get 3.4375. That's correct.
I got 3.42559.
3.42559.
Yeah.
Alright, probably quite close, 3.4. 3.4 quite close.
Okay.
Okay, so once we get the area A, right, means cutaway area. Now we want to calculate A1, this area. Alright, determine area A1. Given shell thickness, T1 is 8 mm. Alright. So our question, right, our question asks, given our project B, they want us to include corrosion allowance, right? So in this case, now you can see over here, corrosion allowance actually added. 2 mm. Alright, so our T1, 8 mm, minus your corrosion 2 mm. So we have 6 mm here now, right? You must include the corrosion allowance. So now our E1, alright, so equal to T1 minus T, and then T lah. So the idea is this. The idea, this is your opening, right? So how they actually measure A1 is half of the diameter here. Alright, so that means the one that we can able to complement, what we are able to reinforce is the half of the diameter here. Right, the distance, half of the diameter means include the pipe. Right, so this part is half of your opening. Right, so you add up the two, the distance is actually equivalent to your cutting. Alright. So what will be your A1? Now I explain to you, right? So what will be the value here?
2,400.
This D, because you see A1 over 2, right? So if let's say A1 means to total up these two, is A1. So what will be the value of A1? The tricky part is normally the corrosion. Some students they forgotten about to include the corrosion. Then in this case, calculation will be wrong. Right. So remember to include the corrosion given to you. Normally, the question will give you corrosion value. So in this case, what happened to this value? A1. 1025. So imagine, right, our cut away area is this. Alright, so now our A1 already 1025. So we have to calculate A2, A3. Alright, so right now we have A3 because of the diagram here. What we saw is actually the pipe insert all the way to the vessel itself. You have A3 A3. But at least you know the approach. Important is after you calculate all the area, A1, A2, A3, A4 must be greater than this guy. 1375 mm square. Alright. So during exam, if you don't get this, if this area is smaller than A, right, then you have to include the reinforcing ring. Reinforcing ring on top of this. Alright, so this part is A1, right? On top of A1, right? Reinforcing ring called A5. Alright, those areas called A5. Unless area is smaller than the cutting area.
So how to get A4?
A4 is the welding.
Yeah, but how to calculate?
How to calculate? Okay, very good. So to calculate, you have to go to KS1210. Okay, let me show you AS1210 regarding this. Okay, now I have to go to 31870. Okay, so over here, this is the equation. If you, let's say, right now, you know how to do A1, as I explained to you. If you don't know how to use A2, A3, right, all these under clause 3.18.10.4 will show you, all right, how to calculate A2, how to calculate A4. Alright. So metal added as reinforcement and metal attachment well, CA5 and A4 respectively. So offhand, I will show you A4 equal to TC2, right? Depending on how many wells you have, number of wells, right? Times TC, right? TC squared.
So number of well, right, means does it both sides equals to one well?
Yeah, in this case, we consider it one.
Still one well.
So this one well, two wells.
So for this diagram is two wells.
So you can see this I have four, right? 1, 2, 3, 4.
So you consider it.
So it means 4 lah. Times TC squared. So how to find DC? Now another question, how to find DC? So you have to refer to this very often. I myself cannot remember so many things. DC.
30 July. 30 July. Commission date. Holy shit.
Alright, so over here they show you DC.
Honestly, just pass me.
Throat thickness.
Yeah.
Got one more actually. I think one more 7.
No lah, I think no.
For this one.
Alright, so
This
my
was the last
advice,
one already.
when you do this
Should be
type of
nice
question,
already.
remember to follow the clause for your easier for you lah. Easier for you to refer to this clause.
2 or 3.
Maybe it's the funniest one. Hopefully don't have.
Okay, we try to do this. Another one just now is the vessel itself. Right now we are going to insert, alright, the nozzle here, the pipe. This is our the air receiver. Alright, you cut opening, then you insert the pipe, right? So now we want to determine the branch thickness. Alright, with the given info here, same steel material used, alright, vessel and nozzle, but now we focus on nozzle. Design pressure 900 kPa, tensile strength 135 megapascal. Alright, opening DO, outer diameter 500 mm. Determine the branch thickness. I also give you the formula. If you look into our course note, they actually given two equations. One is outer diameter, one is inner diameter. Alright. So outer inner diameter will determine positive or negative P here. So give it a try. Important, I want you to have a concept.
So for this one, these two equations, what are the two conditions? Or two?
If let's say you are given DO right now, our over here they show us DO right. So easier is that you don't need to know the thickness of this right.
Oh, right. So in other we have given DO or
Yes. So easy for you to apply because just now our formula for the vessel is this. Anyone get the solution? Similar to previous one is 1 just now. So this is a question I just want you to know, right? The thickness of this TB, the smaller TB, is to withstand the pressure. Alright? So when you select the material for your nozzle, must be greater than this value, right? Because this one will determine later, right? When you work on your work on this. This is your branch thickness. Alright, this is your branch thickness, the smaller TB. and then your branch thickness TB and this one. This is your actual thickness of your branch. Alright, this one is your thickness, branch thickness that withstand pressure. Right? This one is your material use. It will be greater than this, must be greater than this. So this part, we talk about this part. TB, smaller TB. Because some students confused about this, why capital T and also smaller t. What does it mean? If you know how to differentiate now, easy for you to do this question. Alright, the real thickness of the material and the thickness that can withstand pressure is different thing. Alright, that's why with this thickness we are able to compensate. Although we cut away this, right, cut away this opening, but the excess, right, the excess of material able to compensate. This is the idea why we do this question. We find out A1, A2, A3, A4 or A5 to compensate the cut away area A. So the smaller t make a difference. The t that can withstand pressure. Right, that's why we are able to compensate. We have excessive of material to compensate these. Alright, so come to the branch, the solution. Alright, is if you plug everything in, you get 1.686 mm. This is the thickness of the branch that can withstand pressure. Design pressure is 900 kPa.
So the one, the F which we want to find.
135.
Question 135.
Yes, my apology, yes, 135. So the value will be smaller bit.
Sorry, can show the solution for the previous question.
Previous one.
Oh.
Okay, I'm going to flash attendance just to do the last take count. If confirm okay, then I will confirm the thing. So just last round of confirmation. Pradeswara is not here. Darren is not here. I don't know how to pronounce these. Anyone can help me to pronounce it. Takashi, Edmund, Daryl, Kali, Chu. Hey, Lawson not here, right? Anyone? I call the name. No response means not here, right? I guess. Go back and do whatever you can. Next week will be the last meeting, right? Then any question we are able to try to solve it out.
We haven't even started yet.
Yeah.
This is any question please ask.